Hello everybody, welcome back to another RUS Copernicus webinar. My name is Miguel Castro and today I will be guiding you through this exercise where I will introduce you the SNAP GPT software, and for that we will be processing a large amount of Sentinel-1 images to derive the extent of rice crops in a study area in Vietnam. So before starting this session, let me tell you the objectives. You will learn two main things. First of all, how to detect rice fields with Sentinel-1 data, and second, how to automatize your analysis using the SNAP GPT tool. So just before starting, be aware that this webinar is being recorded and that you will be able to visualize the video later on, since it will be published in our YouTube channel, but I will give you more information about that later. So let's quickly move to the outline of this presentation. As always, we will first cover the study area. We will then comment a little bit the use of remote sensing for this type of application, for rice mapping. And then we will describe the RUS service, and right after that we will start our exercise using the RUS Copernicus virtual machines. At the very end we will have some time for Q&A session, more or less 20 minutes, depending also on the amount of questions you have. So the first thing we will do is actually have a look to our study area. So in this occasion we are traveling, let's say, to Vietnam. So Vietnam, among other things, is the world's 5th largest rice producing country. Rice production has continuously increased from 25 million tons in 1995 to almost 40 million tons in 2010. This increase can be attributed to some expansion of rice harvested area and higher yield. The use of input-responsive modern varieties of rice, sufficient fertilizer, and an increase in the proportion of rice area under irrigation account for the high yields in recent years. More in particular, if we focus on the Mekong River Delta, which is going to be our study area for today, it is here where Vietnam produces most of its rice. The other rice growing regions are the Red River Delta, the Northeast, and the North Central Coast. The Mekong Delta has 3 major cropping seasons: spring or early season, autumn or mid-season, and winter or long-duration wet season crop. And the largest rice area is cropped during the autumn season. I'm telling you all this information about the seasons because, as always, when dealing with agricultural applications, it's very important to understand the growing cycles of our crops in order to plan our acquisitions. So if we now go a little bit into the background of remote sensing in the domain of rice mapping, well, first of all, considering the extent and significance of rice, it is fundamental for decision makers to have proper information on the evolution and status of the crop. One of the key differences between rice fields and other crops is that rice fields are usually inundated during the planting and vegetative stage, and detection of this is a key element of most remote sensing rice detection algorithms. Most paddy fields experience agricultural inundation before crop establishment, which is different from lands covered with other crops, such as maize, beans, or vegetables, which are also cultivated in this area. Low SAR backscatter during the transplanting stage and a high backscatter during the early growing stages result in large and rapid changes in the temporal SAR backscatter profile, and this feature can be utilized for discriminating rice from other crops. And this feature is actually the one you can see in this very nice image from MVSAT from 2007, where basically they used multi-temporal false color composition, and they took advantage of this difference in backscatter in the SAR signal coming from the rice fields, since at some point they are flooded and at some point they have a very high response. So I know you are already familiar with Sentinel-1, but let me give you a very brief introduction about this satellite. So for this exercise, as I said, we are going to be using C-band SAR data provided by the Sentinel-1A satellite. The Sentinel satellites are included in the space component of the Copernicus program of the European Commission and the European Space Agency. The Sentinel-1 mission is formed by a constellation of 2 twin satellites faced at 180 degrees to each other. It is an active sensor that works on the C-band, and it provides data with a short repeat cycle and with different imaging modes. So that's all for our satellite. Now let's have a very brief description about the RUS Copernicus service. So first of all, RUS stands for Research and User Support for Sentinel Core Products. It is an initiative founded by the European Commission and managed by the European Space Agency, with the objective to promote the uptake of Copernicus Sentinel data and support research and development activities. The service provides a free and open scalable platform in a powerful computing environment, hosting a suite of open source toolboxes pre-installed on virtual machines, which allow you to handle and process the data derived from the Sentinel satellites. So what does that mean in other words? Well, taking into account the large amount of data produced by the Copernicus program, the challenge is no longer data availability, but rather data storage and processing capacity. To solve that, RUS Copernicus offers virtual machines so that you can have the appropriate environment to handle your data. So in addition to that, RUS Copernicus also provides a specialized user help desk to support your remote sensing activities. So if you have doubts about how to process Sentinel data, you can come back to us. You can be in communication with us via chat, via email, and we are just there to help you in your processing. And last but not least, RUS Copernicus also offers a dedicated training program. So we organize webinars and face-to-face. Actually, you are in one of those training activities. This is a webinar. And of course, we organize from time to time, more or less every month, face-to-face events for people to attend and maybe get to know a little bit more advanced techniques. So you can find all the information about the project in our two websites. So I will not go through them since we have quite a heavy agenda today, but feel free to explore them if you want to know the details of the program. As I said at the beginning, this video is being recorded and will be published. It will be published in our rustraining.eu portal, but also in our YouTube channel. So if you are more familiar with YouTube, you can just subscribe to our channel, and there you will find the recordings of previous webinars in case you have missed them. So let's now move to the RUS Copernicus VM. I will show you very quickly how to access it. So here I am in the RUS VM, in the RUS Copernicus portal. And basically, once you become a user, you register. Remember, this is for free. You can request your virtual machine and access the VM. So if we click here in Access My Virtual Machine, we will just access the VM. And this is the environment we have. So let me just zoom in. So this is a Linux-based virtual machine. It's based on Ubuntu. And as you can see, it contains already all the software installed and ready to use. So you basically have the software, you have your internet browser, etc. So let's start the exercise, and for that we need to show the data download. So I know you might be familiar with downloading Sentinel data, but maybe you are not familiar with the way I'm going to show you. Because today we will be always trying to focus on the automatization of the processing we want to do. And the first step starts by automatizing a little bit the download process. So let's go to the Copernicus Open Access Hub, and I will show you how we can use a download manager to handle our process. So we go to the hub, and the first thing we need to do, of course, is log in with an account. So if you don't have it, you can create it very quickly. So I will log in. So remember, we are working in Vietnam, so let's go to our study area. It's in the south of Vietnam, in the delta of the Mekong River, and more or less our study area is here. So the next thing we have to do, as always, is to put the parameters of our search. So in this case, we want to analyze a time series that will start at the beginning of March 2018 and will finish at the end of December 2018. So let's just put the specific dates. So beginning of March until the end of December of the last year. Next, we know we want Sentinel-1 data. We want to use only Sentinel-1A, and this is because for convenience, I want to have images with the same acquisition geometry. I know I want to use a GRD product. We are only working with the amplitude information, not the phase. And then to make sure that I narrow down a little bit the search, I will use the relative orbit parameter to reduce the results. So in this case, we are using the relative orbit number 18. I will show you later how you can find out this number. So let's run our search. And basically what we will have is the list of results that match our query. So nothing very special. So usually how the way you would proceed, let's say in a graphical way, would be to click on the product and download it as a regular internet download. However, what we want to do is to use a download manager that is called ARIA or ARIA 2, and this program will handle all the download process for us. And for that, the first thing we have to do is to add the products we want to our cart. So I see the search is taking a little bit. So, okay, there it goes. So if you want to download a specific product, you would click here. But what we want to do is actually download a lot of products. We will process a very long time series of Sentinel-1 data. So we want to automatize this a little bit. So to add a product to the cart, we just click here. And now if I go to my cart, I have already loaded a few products into my cart. You see I have a lot of them. So the first step is to download this specific cart. And for that, we click on the arrow here, and the cart will be downloaded into our downloads folder. Remember, it's always within the virtual machine, not our computer. So let's go to the downloads folder and let's see how we manage this. So now what we have here, I have a duplicate. It's the cart that has been downloaded. So the cart is basically a metaphor file. It's a file that contains a link to the specific products that I have selected before. And what I want to do is to use a download manager. So a download manager, in case you don't know, it's a computer program dedicated to the task of downloading standalone files from the internet for storage. And as I said, for this exercise, we will use ARIA2. ARIA2 is a lightweight multi-protocol and multi-source command line download utility. So basically a program that downloads things for us in a simpler way. So how to run ARIA2 in the RUS Copernicus VM is actually very easy. Remember, the VM comes already ready to use for the user, so you don't have to install anything. What we need to do is to write a specific command in our terminal that I have here. You will be able to do it later yourself. So let me put it here and I will explain you what this is doing. So this is the terminal. We will be using the terminal later on a lot, so it's good to start. And basically what we are telling here is let's launch the program ARIA2. Let's log into the Copernicus Open Access Hub. I have here a dummy account that will be deleted after this webinar. So for example, my username is RUS and my password, well, you see it. And then I have a specific parameter that tells me that only 2 products can be downloaded at the same time from the hub. This is, as you know, a limitation of the Copernicus Open Access Hub. Only 2 parallel downloads are allowed per user. And the last thing is the file, and the last thing is the name of the file that contains the links to the Sentinel-1 images I want to download. So what we need to do, first of all, is to open terminal in this folder. So I can just, in Linux, you can just right click on the folder and open terminal. So now we are in the downloads folder in terminal, and now we just need to paste our command for ARIA2 and press enter. If I press enter, you see that the download process is starting, and basically the download manager will take care of everything. In this card, for this exercise, we will be processing, if I'm not wrong, 18 images. So basically it will download the 18 images automatically. As soon as one of the images is downloaded, the next one will start, and I can just leave it and come later once it's finished. So I will stop the download process because I already have my images downloaded. So I will just close here and just remove this from my folder. So let me show you actually the data. I have it here in my folder, and as you can see, okay, we have 24 images. I was wrong before. So today we're going to be processing 24 images, and as you can already imagine, if you want to do it manually one after the other, that will take a lot of time. That's why we want to automatize things by using GPT. So the way I'm going to proceed in this exercise is that I will show you the pre-processing steps that we need to apply to every image. I will use one as an example, and then the same is applied for the others. Remember that when working with SAR data, it is always required to do some pre-processing steps until the image is ready to use for our main analysis. It's not like Sentinel-2 where you download the image and you can already run like a specific classification or something like that. With SAR, we need to apply some pre-processing steps. So let's go to SNAP. SNAP is the dedicated software developed by ESA to handle the Sentinel data. And as you can see, it has, if you're new to SNAP, it has let's say 4 main areas. We have here the product explorer, where the list of products we are working with appears. We have some quick menus that help us to understand the data we are working with. In this case, I have the world map that prints the extent of the image in the world map. I have the display of the image. In this case, is the amplitude VH. And I have here in the top menu all the tools I need and algorithms to process my data. So in Snap you can run the specific algorithms one after the other in a manual way, but you can also build a graph that contains all the steps that are required to process our data. So for that, we need to open what is called the Graph Builder. So we can go to Tools, Graph Builder, and by just right-clicking on the white space, we can access all the operators that are available within Snap, and we can add them to our graph. So for example, the first step we will do is to update the orbits of the metadata related to the orbits of the image. And for that, I would add the operator apply orbit file. Once it's added, I just need to put it in the right place and connect the previous operator to it. So in order to save a little bit of time, I will open directly the graph we will use today, and I will explain you the steps we are running. So I have my graph saved already, and this is the chain we will be using today. So as I said, the first thing we are going to do is to update our orbits. So the orbit state vectors provided in the metadata of a SAR product are generally not accurate and can be refined with precise orbits, which are available 2 weeks more or less after the generation of the Sentinel product, Sentinel-1 product. The orbit file provides accurate satellite position and velocity information, improving the analysis that requires satellite information to be as precise as possible. So this will be our first step, and you see that for every operator that I add in my graph, I have a specific tab below that allows me to change the parameters in case I need. In this case, we can leave the default values. The next step will be the thermal noise removal. Thermal noise in SAR imagery is the background energy that is generated by the receiver itself. It skews the radar reflexivity towards higher values and hampers the precision of radar reflectivity estimates. Level 1 products, such as the one we are using today, provide a noise lookup table for each measurement dataset, provided in linear power, which can be used to remove the noise from the product. And this is basically what this operator will do. The next step is a fundamental step in SAR processing, which is calibration. So the objective of SAR calibration is to provide imagery in which the pixel value can be directly related to the radar backscatter of the scene. The power of the received radar signal also accounts for factors such as antenna gain, system loss, relative orientation of the illuminated resolution cell and sensor, etc. This introduces a significant radiometric bias in the SAR image. The radiometric calibration can be done by calculating the sigma naught or backscatter coefficient. And absolute calibration also considers all the contributions in the radiometric values that are not due to the target characteristics. This permits to minimize the differences in the image radiometry and to make any image obtained from different incident angles and ascending or descending geometries comparable. So in this case, we are going to be deriving the sigma naught or backscatter coefficient, and we will leave the remaining options as default. Our next step will be terrain correction. So because of the side-looking geometry of a SAR system, every target located on the terrain being observed by the radar will be mapped onto the slant range domain. Moreover, due to the topographical variations of a scene, SAR images are likely to be affected by geometric distortions, such as foreshortening, layover, or shadow, for example. The terrain correction is a process by which SAR data are converted from the slant range to ground range geometry and in a defined cartographic system. So in this case, the only parameter we are going to change here is the map projection. We are going to take advantage of the fact that Snap allows us to set the projection based on the UTM system. And if you click on the map projection, we can go down in this menu and select UTM WGS automatic. So basically what will happen is that Snap will locate the image or the extent of the image in the UTM grid, and it will select the appropriate zone for this location. In this case, as you can see, it's UTM zone 48. And also for visualization purposes, I'm removing the option mask out areas without elevation. Basically, if I select this option, all the areas that according to a digital elevation model are at level 0, meaning C, they are removed, they are masked out. But for visualization, I'm not using this option. The next step of our processing chain is to do a subset. In this case, we are doing two types of subsets at the same time. First of all, we are splitting the polarization into two independent files. So in the first subset, I'm selecting only the VH band, And in the second subset, I'm selecting only the VV band. But at the same time, I'm doing a geographical subset. I'm reducing the extent of the image. And for that, I'm using coordinates in the well-known text format, which you can find here. And you can see that my new study area is, the new extent of the final product is much more smaller than the original product. Of course, this is because I'm interested in this specific area, but also remember, processing the full image will take more time, will take more processing time and more storage capacity. So I terrain correct my image. I divide the file into the VV and VH polarization as independent files, and I reduce the extent of the product. And in the end, I just write my two operators, my write operators that will save the product. So once we reach this point, what would be the regular way to proceed? Well, basically, once you have this graph, you identify an input product. For example, the image I have here open in Snap, you would directly click the run button, and then the image will be processed according to this graph. However, today I want to show you another way of processing images, which is by using the GPT option of Snap. GPT stands for Graph Processing Tool, and it's the command line interface of Snap. It's just a different access point to the Snap software. Instead of doing it via the graphical user interface, which is this software here, we will do it through the terminal, through the command line. So how we would proceed? Well, first of all, let me show you how GPT looks like. If we open the terminal window of the virtual machine and we write GPT, we can have a look to the output of this. Basically, what the program gives me back is the list of operators that is available. This is almost the same amount of operators that we can find in the menus of the graphical interface. So for example, I can write GPT, the name of a specific operator, subset in this case, and write the parameter h, which will give me the help of this operator. And I can see the details of this specific operator. For example, for the subset, I can see that I have the description of the operator, so what it's doing, and then I have the list of parameters that are allowed and that can tune the effect of this operator. And at the very end, I have the XML format of this operator. This is very important, but later on I will show you why. But this is a key element of using GPT. So how would you run a graph in GPT instead of in the graphical interface? Well, I have some slides to show you that. Well, to run a Snap graph in GPT directly, the first thing you have to do is to go to terminal and write GPT and then the path to the graph. Be aware that since the RUS Copernicus VMs are ready to use, it is enough to write GPT in the command line. This will trigger the action to launch the GPT program. If you are in your own computer or if you are in an environment where GPT is not recognized as a command, you have to set it as an environment variable. So, for example, what we would write is GPT, the path where we have saved the graph. In this case, this is the path where I've put it, and then the name of the graph. So let's see an example of that. I will go here. And basically, you just need to write GPT and then the path to the graph. So in this case, my path, I've stored it before in the aux data folder. This is it. And I can just write the path and the name of the graph. If I click enter, the process will start. And now you can tell me, well, and where are the images, where are the outputs going to be saved? Well, they will be saved in the path that I have specified here in my graphical interface. So if I go to my RISE mapping, if I go to this specific path, which is here, you can see that the process has started and the first product is being created. So I will cancel this option because this is not what we want to do. But now you can tell me, well, this looks good, but is actually not a very good advantage because basically I can build my graph and click run and I'm done. So why should I do this? Well, of course, it's not very convenient yet, but you need to understand how to run in the individual graphs so that you can understand how to do batch processing in GPT. So what we have to do now is to actually have a look to the graph that we have created. So here we have, let's say, the graphical representation of the graph. Let me rearrange the windows a little bit for convenience. So here we have the graph we have created, but actually this is an XML file that is being created by Snap. I have saved it here, and let's now have a look together. So if I open this with a regular text editor, you can see it. So if you're new to programming, or if you're new to the terminal or the command lines interface, you might think that this is a random document that is being created and that there is nothing here that you can read and understand. But it's not the case. This is a standard XML document. It follows the XML syntaxes. And basically, for every operator that we are adding in our graph, so for the apply orbit file, for the thermal noise removal, there is a specific XML code that is being added to the document. And you can find always the same structure. For example, I have here in line number 3 the read operator. The read operator starts with the node tag, and it will follow until the node tag is closed. So here I have all the information about my read operator. Next, the apply orbit file operator starts, again with the opening of the node tag, and it finishes with the closing of the node tag. After the apply orbit file, as we can see on the graph, thermal noise removal. So we have the same structure. And after thermal noise removal, well, you see it already, calibration. So for example, here we have calibration. So within this specific chunk of code, we have a lot of things that are being said. We have all those parameters. And now you can tell me, well, what are those things that I see in between? Well, those are the options that you can set for this specific operator. For example, if I go in the graphical interface to calibration, I see that I have the option to graphically select the output. I can select sigma 0 or gamma or beta. So if I go to my XML document, I can see that because I have selected sigma naught to be the output, in line 46, I have the output sigma band parameter set to true. For the gamma and beta parameters, they are set to false because I didn't select them. So manually, you could come to the XML document and write true, and this will output the gamma band as output of the calibration. However, this is not what we want, so let's set it to false. So far, now we have a clear idea of all this document, and now if we go back to the read operator, you can see that the read operator also contains specific parameters. In this case, there is one that we have to pay attention, which is the file parameter. This option here, this parameter here, is identifying the image that will be processed by the graph. And as you can see, now it is pointing to a specific path where I have one image that I want to process. And if I go down, I can also locate my write operators. For example, here I have one write operator. And again, within the write operator, I have the file parameter that is pointing to the output path and the output name of the chain. So what I need is this graph to become dynamic. So far, this graph only allows to process one image, the image that is being defined on the top part here. So this graph so far is only able to process this specific image, but this is not what we want, because if you remember, for this exercise, we want to process 24 images. So we need to do something about it. We need to convert the graph, which is now static, into what I call a dynamic graph. And how to do that? It's very easy. What we have to do is to create a variable. So instead of having, let me minimize this, instead of having in the read operator a path to a specific image, I will remove this, and now I will create a variable. Variables in XML, if you don't know, they are defined first of all by the $sign. So I add the $sign. This tells the computer that whatever comes after, it's a variable. And now I will put a name to this variable. So you can name the variable as you want, it doesn't matter. In this case, I'm naming it input1. This is the name of my variable. And now I have to go to my output, to my write operators, because the output, sorry, the write operators, which I have here, for example, here, my write operators are now set to create only a specific output according to the image that was set as input before. However, this is not what I want. I want my output to be dynamic so that it saves the output according to the image that is being processed at the specific time. So I will come here and I will remove the path and create my variable. Again, $, and now I'm calling this output 1. And I have my other write operator. Remember, we have 2. So we have here the second one. You see it starts with write to. And here I see that it also contains a specific path to a specific output. I will remove this and create another variable that I will call $output2. So once I have this, I have now converted my graph into something dynamic. Now there is no specific link to a specific input, there is a variable. And this variable, it can change, and we will see later how to do that, so that we can batch process all our images. So if I save this, so I go to File, Save, and I go back to GPT. So if I repeat the same procedure and I try to run this, it's going to fail, because of course the read and write operators, they are not pointing to any image. So far I have something that is called $input1. Remember, if I go here up, I have input1. So Snap doesn't know nothing about that. This is not a specific path to any Sentinel-1 image, so it's failing. So what we have to do is a small trick to tell GPT what should be the value of this variable. So instead of calling my graph like this, I'm going to save it with a different name. I will save it with the same name but underscore GPT. Actually, I have already saved it, so I will not do it, but you have to do it if you're repeating this exercise. So what we have to do is to tell GPT what should be the value of this variable. So how to do that? Well, we come here to the terminal and we write GPT, sorry, yeah. So we write GPT, and the next thing, as I said before, is to write the path to the graph. So in this case, our graph now has a different name, which is this one. So I will just drag and drop. So GPT, the path to the graph, and now I have to tell the computer what should be the value of the first variable I have, which is input1. So how to do that? Well, first of all, we add dash, then we add capital P, and this is very important. This is the way you refer to a variable in GPT. So in the XML document, you create the variable by putting $ and then the name. Later on in GPT, when you want to call this variable, you write dash capital P, and then you write the name of the variable that you have set before. In this case, my variable was named input1. So P input1 equal, and then you need to set the value of this variable. So remember, this is the input of the image we want to use as input. So the value of this variable has to be the path to a specific Sentinel-1 image. In this case, I want to process the first image of my time series. So I just drag and drop here. And now I'm telling that the P input value equals this specific path to this specific Sentinel-1 image. So we are done with the first variable. Now we have to do the same for the output1 and output2 operators. So remember always that we are saving two outputs, one for the VV polarization and the other one for the VH. So we just repeat the same procedure. Since we have created a variable that was called output1, then we call it by writing P output1 equals, and then we specify the path where we want to save our images. In this case, my path is going to be, I'm going to create a specific folder, for example, webinar, and my path is going to be this. So this is the path, and then I have to give a name to this output. So I will call it, for example, I will use the sensing time. So this image is from 2018, March the 7th, underscore VH polarization. This is my first output. Remember, I had a second output, so I will do the same. Dash P output2 equal, again, the same path. And now I will call this image the same 2018-03-07 VV.dim. You can write the .dim. This refers to the format which we are using. By the way, is the default format used by Snap, the bin-dim-up format. But you can also skip it. You could also write this because by default, the operator knows which is the format that should be applied. But okay, just for redundancy, I'm writing it here. So now if I run this, what will happen is that the process will start, and now I have an error because I did something wrong for sure. Okay, it doesn't matter because I have here a backup, so there's always a plan. So what we have to do, just come here and I will just copy paste this. So just as an advice, if you are new to scripting and coding, there's always something that goes wrong, especially with typing. So yeah, don't panic about that. It's just a matter of reviewing everything. So now the process has started, good. And basically you can see that the graph now knows what should be the input variable, because now it knows, okay, my variable that is called $, wait, let me show it to you while I speak. Now the graph knows that my variable input1 should have this specific value that I have specified before, and that my output variable that I have defined here also has a specific value. So now you can tell me, well, look, Miguel, this looks great, but I still don't see the advantage of that. I mean, I could run the graphical interface of Snap and process this without any issue, and I would have the same result. And I would tell you, you are right, but I'm not finished yet. And now we come to the last step where you will see actually the advantage of using this approach. So let's cancel this. The image is being processed. Oh, okay, if you want, we can wait to prove that it's happening. So basically, you see here my image being processed, and if we wait for the process to finish, I will be able to open my image in Snap. So the process is finished, done. I can now close, and now I can just open this in Snap, and you get the output. But remember, our objective is to process all the images we have in batch mode. Batch mode, I mean in an automatic way. I don't want to be changing parameters every time I change my input image. I want the computer to do this automatically. And for that, we will be using a specific script, a bash script, that will automatize all this process. So I will show you the script and I will explain it little by little, since I know that we have some beginners here, but that's fine. So this is the script we will be using. Don't panic if you're new to programming. It's very simple. So let's have a look to what's happening here. Well, in our script, the first thing we are doing, let me just reshape the windows so that we have a better view. Okay, so the first thing we are doing in our script, you have to see the script as a set of instructions to the computer. So the first thing we are telling the computer is the definition of some variables. You can see it here. So we are telling the computer there is a variable that I'm going to call path_s1 that is equal to a specific path, which is here. If you recognize, this is the same path as this one. I'm just telling, okay, path S1 is the specific path to this folder where I have all my Sentinel-1 images that I want to process. The second path I'm creating, the second variable I'm creating, it's called path_vh. And this is the folder where I will want to save my outputs later. So it's basically the output directory of the process. And since I know I'm creating independent files for the VV and VH polarization, I'm creating two output directories, one for the VV polarization and the other one for the VH. So that's why you see here two paths, which are basically the same except for the end. Here is VV and here is VH. Okay, once I create my variables, I go to the next step, and I create all the variables. The first variable is called old_end, and it's equal to .zip. You will see later how we use this. Then we have the VH variable that is called VH equal, well, you see it. And then we have the VV pol that's equal to _VV. So far, nothing very complicated. We are just declaring some variables. So what's going to happen next? is that we are going to initiate a for loop. So what do I mean by a for loop? Well, basically we are telling the computer the next. We are telling the computer, go to this specific path, and I'm going to demonstrate it live. So we are telling the computer, I have this variable called path S1. I click enter, and this variable equals this specific path. And then I'm telling the computer with this command here, you have to create a list that contains all the files in this path that start with S1. So I will highlight it. So I'm telling the computer, go to this specific path, which is the variable path S1, and look for all the files that start with S1. Then there is some text that I don't care, and then the file should finish by .zip. If you remember, all the Sentinel images, or let's say the Sentinel-1, Sentinel-2 images, they follow what it's called a naming convention. So all the images follow the same structure in the way they are named. And we can take advantage of this naming convention to create some scripts that perform automatic tasks. So you can see that my Sentinel-1 images they all start with S1, then there is a lot of things in between, and then .zip. This is a common structure. By the way, if you want to know more about the naming convention of Sentinel, just Google naming convention Sentinel and you will find it. So let's demonstrate what this thing is doing. If I run this independently, let's see what happens. So I just run this, and what you see here is that the computer is telling me, okay, I've gone to this path, and I'm giving you a list of files that fulfill your requirements. Basically, here what we see is the 24 images I have. So the next thing I'm doing is I'm initiating a for loop. So for every element of this list, for every image of my folder, I will do a specific amount of tasks. The first thing I'm going to do is to extract the sensing time from the image, and I will use this sensing time to use it as the output name, so you will see it. The first thing we have to say is, okay, I is equal, so I'm creating a variable that's called I, and for example we can say, okay, I is equal to this specific image. So let's actually run it like this. So I am saying the variable I is equal to this specific name of a Sentinel-1 image, and then here I'm creating a variable that is called n. So the first thing I'm saying is take the variable I and remove everything that is after the dot. So basically, if I do this here and I just echo my variable, so this is like printing the variable, I can see that now the computer is telling me, okay, I have removed the .zip from the name you gave me before. The next thing I'm going to tell the computer to do is to remove everything that is after the T. This T here. You can see here I'm putting a T. So I'm telling the computer, okay, I don't care about anything that is after this T. So I just run this command, and again I visualize the result. And we can see now that, sorry, I was wrong. It's this T here. So what I can see now is that the computer has cropped the name, and now it's giving me only this information. But my interest, remember, is to extract the sensing time. You will see later why this is relevant. So now the next instruction I'm telling the computer is, okay, that's fine. Now what I need to do is to extract everything that is after this underscore here. So I will just copy paste this and visualize it. And you can see that now, using this very simple script, from the Sentinel-1 image, I'm extracting the sensing time. And the sensing time is something very useful when you work with time series, because basically it's the key information you want to keep. You want to know when was, if you have 24 images, the main thing you want to know about them is the sensing time of them, so that you don't get lost. So with this very easy task, with these 3 lines here, we are doing that. So the next thing I'm doing in my script is I'm printing the date. So if you write date, the computer is telling you the specific time. And then I'm calling GPT. So I call GPT the same way I have explained before. I write GPT, and then I write the path to my graph. Then I have to declare the values of the variables. You remember we created the input variable, the output variable, so we have to declare those names. So I have here my /p input1 equal, and then equal $i, sorry. So what I'm telling here is, okay, in the list you created before, so if I go back to my terminal and I print this again, let me show it to you. So I'm telling for every element of this list, so for I in the list, put every element of this list as the value of the variable input1, and then for the output I want to put together the variable path vh. So I'm going to do it live with you. So if I declare my variable path vh here, then I will put together the variable n. So in this case I will say n equal, for example, 2018-0307, and then I will say that vh_poll, the variable vh_poll is equal to _vh. Sorry, here. Okay, so now if I put this together, what you will see is that basically the computer is putting the three values together and it's telling me, okay, the value of the output1 variable will be this specific path plus n, so the sensing time, plus _vh. And I will build the value of the output2 variable in the same way. So in this way, I'm automatizing the creation of the output names, and I'm also automatizing the input1 variable. So the way to proceed once you have this script is to save it, of course, so file save. And now we can just go to my terminal. I will put it here, and you will see that if I go to my processing folder, the only thing we have to do is to run this script. So how to run this bash script is very easy. We just put the path to the script and press enter. So right now the computer is starting, and as you already know, what's happening here is that every single image of my original folder is being processed and being used as input variable. So the first image is being processed and the first output is being produced here for the VH polarization. And if I go to the VV folder, I have the VV band. So, and this is gonna be automatic. So all the images of my folder will be processed. And it's at this moment that you can see the advantage of using this approach. Of course, before it was just an introduction, but by using a very simple bash script, you can automatize it and you can do batch scripting in a very, very easy way. Of course, first of all, you have to create the script, but once you have it, it's something that you can reuse for different projects and you can automatize things. Of course, there would be another level of performance, let's say, where you could link the download of a product to trigger an automatic processing, but we will leave that for a more advanced webinar if you have interest on that. So just to demonstrate how the script is working, let's wait until the image is processed. It doesn't take that much of time. And you will see that as soon as the first image is processed, the second image of my folder will be ingested by the script as an input1 variable, and then the appropriate outputs will be created. So let's have a look. If we look here into the folder, we see that as soon as the first image is finished, the second image starts, and now the output will appear here in very few seconds. There it goes, yeah. So now we see that the image 2018-0319 VV polarization is being produced, and the same for the VH polarization. So since we have 24 images, let's not wait until it's finished. It doesn't take that much, but let's keep this process because I've done it already. So I will show it to you. I've run this process before, and I have it here. So in my VH, you can see all the products have been processed here. I have also some extra files that I will explain you later, but basically I want now you to pay attention to the fact that we have all our images processed. And you can see they have been processed in a very easy way. Once you have the script, the only thing you have to do is to go to terminal and say, hey, or you can say, computer, process this script for me, and you can just wait and relax or do other things. So once we have our images processed, we can continue our analysis, because we have to remember that we want to map rice in Vietnam. So what we do now is we have all our images processed and we can continue our analysis. And for that, we go back to SNAP, and I'm going to open a session that contains the files we have processed. So let me go to open session, and I will just open the VH. So what I'm doing here is I'm loading all the outputs of the VH polarization, so the 24 VH bands, to show you what are the steps we need to do now. Something you need to know about SNAP is that when you work with time series and you open a lot of products at the same time in SNAP, SNAP will not open them in chronological order. And this is a disadvantage, and it's something you have to know to avoid issues. So basically what has happened here is that I've manually opened the 24 products in chronological order, and my next step is going to be to create a stack. But first of all, let's maybe show the result of the processing we have done. So let's visualize the first image. So meanwhile, let's keep moving. So as I said, the next thing we want to do is to stack all the products together, and we want to create a stack to allow further processing. So to create the stack, it's very easy. We just need to go to Radar, Co-registration, Stack Tools, Create Stack. The first thing we have to do in this option is to click in the Add Open Products button. So this will load all the products we have open in SNAP, and we can also refresh the metadata to have more information. The second tab will allow us to control the parameters of the stack operator. So the first thing is we set the resampling type to nearest neighbor in case there is some resampling needed. We set the initial offset method to product geolocation, and finally we just click on the find optimal master so that the computer picks the layer that prefers that is better to be used as master. And in the third tab, we have the write details. So here we can set the output name and the output directory. So let's set the output path to the processing folder, and we would be ready to run the process. I'm not going to run it since it takes some time, like 30 minutes more or less, yes. So let's skip it. We don't have 30 minutes for that. So I will close. And also remember, we have to do the same for the VV polarization. So far I'm showing you the VH, but you would have to open the VV files and do the same. So let's actually open the stack. And by the way, this is the result. And now you can tell me, well, it looks kind of dark, not very useful. But of course, this is due to the color stretch. So of course, you can play with the color stretching and you can produce an image that looks better. Basically, we see the result of the calibration, the terrain correction, the subset, etc. We can see the river, the coast here, and you might suppose those are rice fields. But so far, we don't know. Okay, so let's close all the products here, and let's visualize the stack. So I close all the products, I don't save anything, and I open the stack. As I said, I created the stack before. So I have it here, the stack for the VH, and I will also, to make sure we don't get lost, I will open the VV one. So here we have the two stacks, and basically the stack, we have not changed anything on the data. It's just that we have created one file that contains in the bands folder all the layers we had before as independent files. So there's nothing here new. The next step we want to do is to run Speckle filter. So in this case, let me introduce you a little bit to Speckle filter. So Speckle filter, or speckle noise-like feature, is a common phenomenon in SAR systems. It is also known as the salt and pepper effect. It confers to SAR images a granular aspect and random spatial variation, and might decrease the utility of SAR imagery by reducing the ability to detect targets and obscuring the recognition of spatial patterns. The source of this noise is attributed to random interference between the coherent returns, since we are using an active sensor. And the principle of speckle filtering is to reduce the variance of the complex speckle scattering and improve the estimate of the unspeckled scattering coefficient. So there are different techniques to run speckle filter. There are different approaches. The first one would be to do multi-looking. You have to remember that Sentinel-1 GRD products are already multi-looked. Just for you to know. I mean, if you want to do more multi-looking, you can, but the images have been already multi-looked. That doesn't mean that you don't need to do speckle filtering, but it contains already a certain level of processing in this sense. The other approach is spatial filtering. So in spatial filtering, what we do is we use specific algorithms that look at the statistics of moving windows around the image and apply specific algorithms to reduce the speckle. I'm not going to go into the, let's say, the algorithm behind the different filters. There is a whole science about speckle filtering, and you can find many references and papers about that. So let's just use it, and if you want to know more, I'll recommend you to check literature. So another thing to mention here is that we are going to use a multi-temporal speckle filtering. Since we have a time series, we are interested in taking advantage of this temporal behavior we have in our data. And the multi-temporal speckle filtering, it's basically the same as applying a single product speckle filtering. It's just that the multi-temporal will apply a weighted average of the selected filter across all images of a time series. So another remark to do is that since we are working in a very flat area in this part of Vietnam, we are running speckle filtering after terrain correction. So you would see in literature that speckle filtering should be applied before terrain correction, since the algorithm is designed to work with the data before it's zero-coded. But since we are using a filter that is, you will see that we are using a filter which is the least sigma filter. It is not that affected by this phenomenon, and also since it's a very flat agricultural area, the changes are not that much. Of course, you can always check the results of both approaches and choose, but just for you to know. So how to run multi-temporal speckle filter? The first thing we need to do is to have a stack product. In this case, we have it already. And the next thing is that we go to radar, speckle filtering, multi-temporal speckle filtering. We set our input product, in this case the VH stack. We save it in the appropriate folder, in this case the processing folder. And in the processing parameters, you can choose the filter you want. Remember I said there's a lot of information about filters. You can see that Snap gives you already several options. In this case, we are using the default setting of Snap, the least sigma filter with a 7x7 window size, etc. So that would be all. Now we would run the process, and then we would do the same for the VV stack. We will not do it since this is a heavy processing step. So let's skip that and let's visualize the result actually. So what I want to show you is actually the result of doing speckle filtering. For example, so I want you to see the difference between an original image, an image that has been corrected for speckle filter, only taking into account that image, and then the result of multi-temporal speckle filtering. I think it's actually a very nice example. So let me open a session that I have already created. I have it here, and let's visualize that together, because you can see the impact of doing multi-temporal speckle filtering. Of course, multi-temporal speckle filtering is only possible if you have a time series of data. So, and the more images you have, the better the result will be. Okay, so let's have a look. This is our original image. Okay, I didn't say it, but I have converted to decibels. I will explain this step later, so don't think about that right now. So I have my original image as it comes from my processing chain. I have my image that has been corrected for speckle filtering without taking into account the temporal profile. Later on we will zoom to see the effect of that. And now I have here my result of the multi-temporal speckle filtering. So I will open the same image. So here we have the three images, and now for the same date. So in this case is the image of 2018 March the 7th in VV polarization. So let's have a look to the result. For that I'm going to link all the views, and let's zoom in to see what's happening. So I'm gonna do like this. Okay, it's coming. So, well, we cannot interact, but I would ask you to make a bet to see what's gonna be better. The no filtering, single product speckle filtering, or multi-temporal speckle filtering. Maybe you have already an idea. Okay, so it's taking a little bit of time. We will see it, don't worry, because I think this is very nice to see and explain. But meanwhile, let's keep moving. So after speckle filter, as I said, the very last step of our processing chain is going to be the conversion to the decibel scale. So what do I mean by decibel scale transformation? Well, basically, due to the high dynamic range of SAR imagery, and by that I mean due to the large range of values we have in a SAR image, the decibel transformation is used, and the decibel transformation, if you don't know, it's basically a logarithmic conversion, is used to, so we use the decibel transformation to improve visualization and data analysis. The transformation will stretch the radar backscatter over a more usable range, which has actually a nearly Gaussian distribution. And if you know something about statistics, you know that the sooner you have some kind of distribution, the better to apply models. So we will convert our data into decibels. I will show you that later, but now let's focus on the speckle filter, and you can see already the effect of that. Remember, here we have the original product. Here we have the single product speckle filter and the multi-temporal speckle filter using 24 images. So I think the results are quite impressive. You can see basically comparing the image in the middle and the one to the right that the linear features are much more visible in the multi-temporal speckle filter. Actually, some linear features are not visible at all in the single product. I'm talking about, for example, those paths here, those lines, let's call it like that. But of course, let's move to other areas. I mean, let's test this. For example, here is also very impressive, the way it worked. Let's zoom in a little bit more, actually, to see the detail. So you can see that, well, you can see it yourself. There's not much to say. Just seeing it, you see the advantages of using multi-temporal speckle filter, if you can, of course. So you can see that not only the speckle is reduced, but also linear features are very well preserved using this approach. I think I will show you a couple of examples more. For example, look at this path or way or line here. It's it's poorly visible in the single product speckle filter. Of course, in the original image, it's much more random, the behavior. So let's actually show other examples over here. Okay, it's coming. Okay, so you can see the influence of that. If you are repeating this exercise, I would recommend you to spend some time here and visualize different areas to see the effect of speckle filter. I think it's actually very, well, very impressive. Okay, so I said that after speckle filter, we had to apply the decibel transformation. So how to do that? Well, those products are already converted into decibels, so I will close them, and I will open the products we had before. So we were so far stuck with our, so we had our stacked product that was multi-temporal speckle filtered for the VV polarization and also for the VH polarization. So let me open it for you. There we have. So as I said, we need to convert that into a decibel scale to have a better range of values. And for that, we just click on the product and we go to raster, data conversion, convert bands to from decibel. And basically here we just need to select the input, set the output name, set the output folder to the processing folder in this case. And in the processing parameters, there's nothing to change. We leave the default, which is basically we want to process all the bands. And we would just press run. Again, I'm not going to do it because that takes time and we don't have it. Remember, we have to do the same for the VV and the VH. So once you are done with one, you have to run the other one. And basically, once you have this, you will end up having the two multi-temporal speckle filter stack in decibels. So I have here my VH product and my VV product as well. And you can see now that if I expand my bands folder, I have them all in decibels. So I can just open one for curiosity. Okay, so far we haven't done anything. We haven't reached the level of processing we want for RUS mapping. We are just preparing our data. We have pre-processed them, and now, yes, they are ready to be used for our specific application, which today is RUS mapping. So for this, we are gonna leave SNAP. We will not use SNAP anymore, and we are moving to QGIS. QGIS is a GIS software, and it's already by default in the RUS Copernicus VMs. So let's go and let's open QGIS. Okay, so what we do now is we need to open all those products that we have processed in SNAP, all those layers that are in decibels, and for that I already have a session open. I have a pre-saved session in QGIS, and I have here all my layers. So basically this is the same point where we were in SNAP. So the first thing we want to do is to analyze the temporal profile of the sigma naught coefficient, the backscatter coefficient, because we have to take into account that RUS has a very specific behavior in terms of backscatter, and it's very relevant to identify crop patterns. So in QGIS there is a specific plugin that it's called Value Tool, which allow us to identify a temporal profile over a raster time series. I have this plugin installed already, so I will use it. I just need to activate it here and enable. And then I can go to my options. I can select all layers, selected layers, and I will select all the VH bands, which I want to take into account in my temporal profile. So I have to do this manually. Yeah. And don't want to miss anyone. Okay, so remember we have 24 products in total. So I will just select all of them. You see that when I reach 24, 25 is already in VV. So far I want to see the temporal profile in the VV polarization. So once I have all these images selected, I can go to my graph and I can just click anywhere on my image, and the tool will display the temporal profile of the pixel value. The pixel value in this case is the sigma naught in decibels, and you can see there is a very specific behavior in this temporal profile. We have, let's say, a higher value that then goes down a lot, and then it increases a lot. I mean a lot. It increases, and then, well, you see the pattern. If you know something about rice production in this area, in Vietnam, they have multi-crop season. So they have several growing cycles over the year, and this is basically what we can see here. Of course, if you match this with the growing cycle, if you match this with in situ data, you can verify that, but by checking literature you will see that this is the case. Again, remember that rice fields are flooded at the very beginning of the crop during the vegetative stage, and right after that there is an exponential growth of vegetation, which causes a change in the backscatter that is coming back to the sensor. Remember, SAR is mainly affected by structural features of the target, not by color or by chemical properties such as optical data. So this is the behavior we can see here, and this is a very nice tool because I can basically click anywhere on my image, and the graph will show me the evolution of sigma naught. In this case, I'm showing you for the VH polarization. You could do the same for the VV polarization, or even for the ratio VV divided by VH, if you have produced that. So far, we see already how Sentinel-1 allow us to have a very dense temporal series and monitor our rice fields and detect when the growing cycle is starting, when the harvesting is happening, and this for decision makers and planners is very relevant, even for the market itself, to know what's happening in the fields. But I want to show you another way of analyzing those images, which allow us to have a very nice visualization of where the rice is being cultivated. Because so far we have a black and white image, and okay, it's not very visible. So we can take advantage of the long temporal series we have and the specific behavior of the starback scattering in rice fields to derive the minimum, the maximum value of the RUS of the pixels in our time series. For that, we are going to use a specific tool that is contained in the RUS package, in the RUS, that is part of the RUS toolbox. So this tool is available in the QGIS, and it's called r.series. And basically, I can just open the tool here, and I can first of all select which are the rasters I want to use for my statistics. So I will click here, and if you are repeating this exercise, you have to manually select all the VH bands we have here. So I will not do it because it takes time, but you have to do it. So once you have all the rasters selected for the VH, you can here select what's the aggregate operation. So in this case, we want to derive the minimum pixel value. So for every pixel, we want to derive what is the minimum value that this pixel has throughout our time series. And we want to save this in a specific location. So I will call it, in this case, minimum. Yeah, well, there's a mistake, but it's okay. Next, we want to derive also the maximum value. So we would change here the option to maximum. And I would call, in this case, maximum. And remember, we are doing so because we know that rice fields, at some point, they have a very low value. We see it here. And at some point in the temporal profile, they have a very high one. And we want to use this as a feature to identify rice versus other land covers. So I've done this before. Remember, you have to do this both for the VV and VH polarization. So I've done this before. So let's have a look. Let me just close everything to avoid any issues. And I will open those files directly. So I have here my max and min, and you can see them here. So this is what you get for the minimum, and this is for the maximum. So now we need a third layer, which will be the difference between the maximum and the minimum. And for that, we use the raster calculator, which is a simple but powerful tool in QGIS. And we will do the maximum minus the minimum. And we will save this in a specific path. In this case, share training, LAND10, and I will save it here, call it difference. And I will just click OK. Remember, we have to do that both. I know I'm repeating this a lot, but it's just for you to not get lost. We have to do that for the VH and VV polarization. So let me show you the result of this operation for both polarizations. I have here my difference, and now let's also open the three files for the VV. So the difference, the VV, max, and min. Okay, so I think they will be open. Yes, okay. There it goes. So here you have the independent layers that gives you an idea about where the rice fields are. But now you can tell me, well, Miguel, yeah, kind of I see it, but still it's not very visible. I mean, you need a lot of local knowledge, and maybe you need to combine the different min and max values. So is there a way to visualize this as a unique map? And the answer is yes. What we need to do is to build a false color image. So how are we going to do that? And this will be the last step of this exercise. Well, it's very easy. We will build just a false color composition. So the first thing I'm going to do is to I will show it only for the VH polarization, but it can be done for the VH as well. It's no problem. So let me just rearrange my my layers. Okay. So to build a false color composition in QGIS, we go to raster, miscellaneous, build virtual catalog, and then here we select the option use visible rasters. We select the option separate, and we save the output in a specific path. In this case, I'm going to save it in here, and I will call it RGB _VH. and enter, and now let's run it. And let's have a look. So here it is. And now we reach the final result. So what you can see here is this false color composition, where by using the minimum, maximum values of the pixels and the difference between the min and max value, we can highlight this temporal behavior, temporal behavior of RUS, where at some point it has a very low value and at some point it has a very high value, with a very high difference also in between. So using this very basic approach, where we are only playing with the visualization of the different bands, we can see very clearly which are the fields that are going through this evolution of having minimum and maximum values, and then concluding that those fields are RUS fields. Of course, you have to take into account that this is not a classification. This is only visualization, and here there is no validation data. So I cannot say this is a RUS field. I mean, most likely it is, but there is no accuracy assessment on this, and proper research would require that actually. But it's a good starting point where you can see the advantage of using the dense temporal series that Sentinel-1 provides, the automatic processing that is done through GPT, and basic visualization tools that can allow you to end up with those results. Remember, you can derive the same visualization with VV, but I've done it, and basically you will see something very similar. So, okay, do it for practice, but once you get one, it's fine. Okay, so that would be the end of the exercise. So let me just wrap up a little bit with some key messages that I want to tell you. So with the new Sentinel satellites, the challenge in satellite remote sensing is no longer data availability, but rather how to store and process all the information. In addition to that, it is necessary to explain how the data can be used and support users in their applications. The RUS Copernicus service is here to solve those problems by providing virtual machines to store and process the data, and by offering a dedicated help desk supported by a team of remote sensing experts to help you in your projects with Sentinel data. So before moving to the Q&A session, let me repeat again that you can repeat this exercise by your own. So you can register as a RUS user, you can get for free a virtual machine, and you can get the tutorial kit of this exercise. Basically, you will get the folder with all the data you need, and you will also get a step-by-step guide in PDF, which contains basically all the steps. Thank you very much for attending. I hope you have learned something new today with the use of Sentinel-1 and GPT and bash scripting. This is the training code of this exercise. In case you want to repeat it, this is our websites, and of course we are in social media, so feel free to follow us if you want to stay tuned with upcoming webinars and face-to-face sessions. Thank you very much, and I'll see you in the next one. Ciao.